Now that we know ROS2 is the prominent platform that we are going to use to build our robots, and we also understand ROS2 is being utilized not only in academics by engineers and researchers, but also in the industrial areas. Now, let's get started with the architectural understanding of ROS2. In our earlier videos, we studied how DDS is a prominent change in ROS2. Let's dive deeper into it. We understand that DDS is not a custom messaging protocol how it was used in ROS1, whereas DDS has been utilized in various sectors that we saw earlier. Here, the major points that DDS brings in is its real-time communication. Real-time communication for robots is very essential because there are n number of data points, there are n number of sensors that bring in a lot of sensory data points. These sensors bring in values that are high intensity, high in volume as well. In such a time, communication in real time is very necessary for our robots so it can take effective decisions. The choice of DDS facilitates modularity and decentralization in network. There is no single point of failure like it was in ROS1. The architecture supports real-time operating system, that is RTOS, and provides guidelines to writing more efficient and secure code, ensuring that critical tasks that have to be taken care are done in the given amount of time constraints. So a simplified example of where RTOS can be used, imagine an autonomous driving car, something similar what Tesla is trying to build. So let's say in this dynamic environment, there's a lot of traffic around you and your car is moving through this traffic. Now all of a sudden, if a car stops, what's going to happen? You have to stop your car, right? But how is this data going to transfer? Your camera is going to sense that, okay, there is a car in front of it and it has to stop, and this data has to travel very fast. And hence RTOS comes over here where it executes even critical tasks like this in a given time constraint. Speaking about security, it's a paramount requirement in the modern robotics systems, especially those operating in public or highly sensitive areas. ROS2 incorporates security at its core. Using DDS, one can offer authentication, encryption, and access control within their robotics system. Now, how does this work? Well, you need encryption, you need access control, and you also need security at sensitive areas. Getting access to a Wi-Fi is still okay, but you don't want them to have access to your robot. So you can have a layer of security on top of this as well. Like for example, if your data is being communicated via a topic, it will only communicate it if the person has the right authentication. So now how this would work? Well, you'll have to enable these features within your robotic systems provided by DDS. Let's take authentication. If the right person is not verified to use a specific data, you won't provide. For example, let's say you're using Paytm to pay a certain vendor. You need proper authentication. It could be your biomarker or a password. Similarly over here, if an engineer or if any person is interacting with the data that is coming out from a robot, that particular person should have a sense of authentication. Speaking about access control, let's say you've bought a new bike and obviously you don't want your friend to use it because you're scared he'll crash it. So that's it. You don't give him the keys. That's access control. Now, lastly, understanding encryption. Encryption is basically decoding something that everybody else in the vicinity shouldn't understand. For example, take Morse code. Well, why is it used? It's used because when two people are communicating, the third person shouldn't understand what the actual data is. And that's encryption. So all of this are available in DDS. One can utilize to enhance the robot's security while building a robot. With all of this, your sensitive data not only remains protective and encrypted, but also if somebody is within the same network, cannot participate or access your data, cannot do any sort of eavesdropping or man-in-the-middle attack. Now, all of this are jargons related to the cybersecurity world. But when we speak about robots, they are important when your robot is communicating over a network. Speaking about modularity and flexibility, well, all these components in a robotic stack are modular and flexible in nature. For example, today I can use a DDS vendor of an X company. Tomorrow, if you think I want to use a different DDS from a different company, I can simply replace it by just one single line. That's the modular and flexibility that ROS2 offers. All of this software is built in such a way that it is loosely coupled and I can interchange and twine anything that I want with respect to my desired output. So an example in terms of replacement of DDS being so modular and flexible, imagine you have a pen. It's let's say it's a gel pen, right? If I simply replace the refill that was blue ink and I replace it with a black ink, isn't that altogether a different ink that you write with? Similarly with DDS, I can use something like fast DDS or a cyclone DDS and I can change between them just like this. ROS2 also provides tooling within its ecosystem. There are tools like CLI tools, visualization tools, simulation, etc. When we speak about CLI tools, these are very handy in nature. If I want to see all the nodes listed in my system, I could simply use a command line tool to list all the nodes available at my disposal. Similarly with visualization tools, I have RViz at my disposal. RViz stands for robot visualization. We'll also interact with this software later on, but tools like this make it very easy and effective while developing. Now you might be questioning, oh, what is CLI tool? Oh, what is Node? Okay, what is RViz? Well, hang on. We'll get into it in our upcoming modules. Until then, let's get back to the design architecture of ROS2. Now, in ROS1, we had a client library called rclpy and rclpy. These were utilized for us as developers to write C++ or Python code to communicate with ROS. Similarly, in ROS2, we have something called as RCL. RCL is the common client library, and these have extensions into Py, C++, and furthermore. Which means you have one single client library called RCL and you can create extensions of it. That could be Python, that could be C++, or even the newest kid in our block, that's Rust. So basically, you could utilize rclpy to write Python code to communicate with ROS, or you could write C++ code and use rclcpp as a client library to interact with ROS. The RCL library is itself written in